All right, here we go for chain rule day 2. So chain rule day 1, we talked about composite functions, and so we're just going to start with some straightforward examples here. This one's going to kind of focus on algebraic simplification. You can see that this example says, do not leave negative exponents or complex fractions in your answers. So let's start with the first one here. So best thing you can do with a radical question is to first not actually take the derivative, but rewrite it. So I'm going to rewrite this as 4x squared 7x all raised to the 1/3 power. So again, I haven't taken the derivative yet, but now if I take the derivative of that, f prime of x is going to be written as, if I do the power rule first, we get 1/3 times the parentheses, so 1/3 of the stuff. Now decrease the exponent on the parentheses by 1. And now chain rule, multiply that by the derivative of what's on the inside, which is going to be 8x plus 7. So if I wanted to rewrite this so that it didn't have negative exponents, and maybe for that matter, I'll also write it so that it doesn't have fractional exponents, I could actually rewrite this so that the 8x plus 7 is in the numerator because that's the positive exponent term, right? It has an exponent 1, so it's 8x plus 7 over the denominator is going to have a 3 for that coefficient right there, right? So 3 times this is going to be underneath a radical. So we have the cube root of 4x squared plus 7x squared, like that. Okay, next example, sine to the 4th of x cubed. So this is going to have multiple parts here, 3 links in the chain for this one. So if I take the exponent of 4 first, right, that's the outermost piece of this composite function. So we have 4 times now sine to the 3rd, right, we decrease the exponent by 1 of x cubed, times, all right, so the second link of the chain is handling the trig function. So derivative of sine would be cosine of x cubed. And the third link of the chain here is now going to be handling what's inside the parentheses. So 3x squared. Again, if we want to simplify that, we could multiply together the coefficient that we have in front, the 4, with the 3 and call it 12x squared times sine cubed x cubed cosine x cubed. All right, example C, another one, just like the previous one, derivative of this one. Again, the exponent on the trig function is the first thing we handle, so we have 3 times the tangent now squared of 5x. Derivative of tangent, so now we handle the trig function. Derivative of tangent is secant squared, 5x. Third link of the chain is the derivative of what's inside the parentheses, which is just 5. And so again, if I wanted to, I can multiply the 3 and the 5 together, call it 15 tangent squared 5x secant squared 5x. All right, example D. We have, perhaps we could do the quotient rule on this one. So low D high. So we have the low is just the, I'll rewrite it as a fractional exponent. So we get x squared plus 1 to the 1/3 D high. Derivative of the top is 5 minus high D low, so the high is 5x. D low is the derivative of the bottom, so we're taking now the derivative of the parentheses to the 1/3. So we swing the 1/3 in front and rewrite it as x squared plus 1 to the negative 2/3 times derivative of what's inside the parentheses, which is just going to be 2x all over denominator squared. So I could rewrite that as x squared plus 1 to the 2/3. So then this is technically a complex fraction because we have a negative in the numerator, a negative exponent in the numerator. So let's clean it up a little bit. So in the numerator, I'm going to factor out the lowest exponent term, common term here. So I have an x squared plus 1 to the negative 2/3 that I'm going to factor out of the numerator. So if I do that here, the numerator now looks like, so if I factor out a negative x squared plus 1 to the negative 2/3, for that one, we just get x squared plus 1. Right, if you think about distributing into the parentheses, if I add these exponents together, I'd end up there. So we have 5 parentheses x squared plus 1 minus, okay, so I'm going to go ahead and multiply these two things together. 5x and 2x multiplied together to be 10x squared. So this is my numerator. And my denominator is x squared plus 1 to the 2/3. So now that I factored out that, I could swing that down to the denominator and get a final answer of f prime of x equaling, up top, I can distribute into the parentheses. We have 5x squared plus 5, and then minus 10x squared. So I have negative 5x squared plus 5 over, when I combine this parentheses with this parentheses, I end up getting x squared plus 1 to the 4/3. So one thing I missed here was this 1/3. We have that being 10/3, which makes us 5/3. So we still have a problem here with this being a complex fraction. Easy way to clean that up is to now multiply the top and bottom by 3 so that I don't have a fraction in the numerator. So if I do that, now I have that this is really 5x squared plus 15 over 3 parentheses x squared plus 1 to the 4/3. One thing that we can actually do on the calculator is we can check our answer. This next feature I'm about to show you only works on a CAS calculator. So a non-CAS calculator can take a derivative at a point. A CAS calculator can just take a plain derivative and tell you what the derivative is. So we have the d dx, so that's the derivative with respect to x of the function. So if I type in the expression that we had for the function, which was 5x divided by cube root of x squared plus 1, and that should do it if I hit enter. In fact, you can actually see this as the answer, and in comparison to my answer, I think it factored a 5 out as a GCF in the numerator. Let's just see. Yeah, I could have done that. Again, just a small detail. So this is one of the benefits of having a CAS calculator, is that can actually give you that information to check your work. Okay, next question, write the equation of the tangent line to the graph of y equals such. So we have on this one, to do the tangent, we need to use the point slope formula. So that's y minus y1 equals m parentheses x minus x1. So the nice thing here is that we're really not focusing on how to find the y1 and the x1. It's provided to us. Sometimes it's not as straightforward. You have to plug in the original function to figure that out, but here we just have y minus 9 equals m parentheses x minus -1, so x plus 1. We have to figure out what m is. And so we do that by finding dy dx, right, or the derivative. So if we take the power rule here, the 2 goes in front. So we get 2 times the parentheses to the first times the length of the chain here is going to be 6x squared plus 0 for the constant. Okay, so now we want to know the dy dx at the point. So we do notation for that. We're using dy dx instead of function notation. We are going to write dy dx with this vertical line, and specifically we want to know it at the x value of -1. And the reason I emphasize the x value is that the expression we had x's only in it. So dy dx. If I now plug in -1, we get 2 times 1 cubed plus 5 times 6 times 1 squared. So working with 1 is super nice. Oh, sorry, it's -1. Still pretty nice working with -1. So in the parentheses here, we have 2 times -1 plus 5. So that's -2 plus 5. So we have 2 times 3, which is 6 times -6, no, positive 6. So we get 36. So we get y minus 9 equals 36 times x plus 1. And again, we could actually check that on the calculator as well. Hopefully this goes correctly this time. So we have, this does not have to happen on this can happen on a regular calculator. So we're doing the variable. We want to know the value at specifically the x value of -1. The y coordinate was not substantial for this one. So the original function or expression that we're finding the derivative again, let me just pull it up, it was 2x cubed plus 5 in parentheses squared. So we're doing parentheses 2x cubed plus 5 in the parentheses squared, and we get 36, confirming our answer. Okay, last 2 questions we're going to do for this video. First one here says, find the points where f has a horizontal tangent. So we want to know where is f prime 0. All right, we want to know this information here tells us where is f prime of x equal to 0. So we first have to figure out what f prime of x is here. So I'm going to do, again, the quotient rule. So low, I guess I'll write it in parentheses, 2x minus 1 in parentheses to the 1/2. D high, to over the top, is 1, minus high d low. D low is now the derivative of this parentheses. So we have 1/2, 2x minus 1 to the -1/2, all over the denominator squared. Well, low squared is just 2x minus 1. We're setting this equal to 0. So a fraction is only going to equal 0 when the numerator is equal to 0. So I really only need to worry about the top here. Okay. So what we need to do, very similar to what we were doing in the previous example, is factor out the common parentheses with the lowest exponent. So I'm going to factor out of the numerator. So I'll change colors up here. A 2x minus 1 to the -1/2. And this is just for the numerator. So we do that, and now the top becomes 2x minus 1 to the first times 1. So I don't even have to write the exponent. I didn't have to write the times 1. I didn't have to write. And then we have minus 1/2 x times nothing. Okay, so this is the numerator now, simplified and set equal to 0. So if we're going to solve this for x, we are going to find where 2x minus 1 to the negative half is equal to 0. And where the square brackets I have here is going to be equal to 0. So if I clean that up, 2x minus 1 minus a half x. When I combine my terms, 2x minus a half x is 3 halves x minus 1 is 0. That's the square brackets I have there. So maybe we'll leave them in there just so you can see where that came from. This can't happen. Right? It's because it's reality. It's 1 over 2x minus 1 and a half. That's not equaling 0 because the numerator is 1. So really it's a matter of this, and that's going to happen. So we have 3 halves x equals 1 multiplied by the reciprocal, so we get x equals 2/3. And to find the coordinate where it's a horizontal tangent, I'd have to find out what f of 2/3 is. So if I plug that all the way back into the original function, we have 2/3 over square root of 2 times 2/3 minus 1. So we have 2/3 divided by the square root of 1/3. That doesn't really look very pretty, does it? I'll even write it like this. That's the y coordinate. If we don't like having the complex fraction in there, we can multiply the top and bottom by radical a third. It just doesn't look pretty at all. So we have 2/3 times radical a third over a third. And now we can divide by keep, change, flip. And so we just get 2/3. The 3's cancel actually, so it's 2 times radical a third. So x equals 2/3, y equals that. So as a coordinate, 2/3, comma, 2 radical 1/3. Really what we're going to emphasize more so in these applications is just the x value. Last one, find the second derivative. Well, it sounds kind of confusing, but it's really just the derivative of the derivative. So we have to find the first derivative. Notation for that is going to be f of x. Some of you might be wondering if we're going to use product rule for this, and the answer to that is no, because we have a constant multiplied in front of the parentheses. So I could just do the power rule. So 4 times 3 is 12 times the parentheses now to the second power times derivative of what's inside the parentheses, which is 2x. To do the second derivative, though, which has this notation where you put 2 prime, 2 apostrophes there, so we call that f double prime. Now I do have to do the product rule, or we could multiply out the parentheses, distribute the 12 and the 2x into the parentheses and avoid it, but let's practice the product rule. So first, I guess I'm going to clean this up here and multiply the 12 and 2x together and call that 24x times x squared minus 5 squared. So now when I do the product rule, we get derivative of the first times second plus derivative of the second. So now it's 2 parentheses to the first times 2x times derivative, just the second term, or sorry, first term, which is 24x. And you could leave your answer like that, or we could clean it up. Doesn't matter when it's free response, but if it's multiple choice, we have to see how we can algebraically manipulate this to match one of our answers. So I'm just going to go ahead and write this as 24x squared minus 5 parentheses squared plus the 2x, and the 24x can multiply together. And we'll call that 96x squared times x squared minus 5 to the first. So that is f. All right, we haven't talked about what the significance of it is, but we'll get there.